Static friction and kinetic friction. Consider an object resting on a horizontal surface upon which a horizontal force F is applied. Let us further assume that the value of F may be gradually increased. At all times that the object remains at rest, the applied force F is balanced by the static friction F sub s. Increasing F also increases friction. However, static friction has maximum value. If the applied force exceeds the maximum value of friction, then the object will start to slide and accelerate in the direction of the applied force. But when is static friction maximum?
Static friction is minimum when motion is about to begin or when motion is impending. When we want to push a heavy object, static friction is the force that you must overcome to get it moving. The maximum force of static friction, or Fs max, is given by Fs max is equals to mu s Fn, where mu s is the coefficient of static friction, the maximum ratio of applied force to normal force, mu s is a dimensionless, and Fn is the normal force on the body from the surface. Once the two surfaces begin to slide over another, static friction is replaced by kinetic friction. Kinetic friction, or F sub k, is found to be proportional to the normal force. The proportionality constant mu sub k is called the coefficient of kinetic friction. The proportion you get when you take the pulling force needed to keep up an object moving and divide that by the force holding the two sliding surfaces together. In equation, we have F sub k is equal to mu sub k times F sub n.
For our first example, a 100 kilogram crate rests on a rough horizontal surface. The coefficient of static friction and coefficient of kinetic friction are 5/10 and 1/10 respectively. What is the normal force acting on the crate? What is the value of the maximum static friction? What minimum horizontal force is needed to start the motion of the crate? What would happen if the applied horizontal force is 350 Newton? What would happen if the applied horizontal force is 550 Newton? What is the value of kinetic friction? We are given that the mass of the crate is 100 kilograms. We have a weight which is equal to mass times the acceleration due to gravity. We have 100 kilogram times 9 and 8/10 meters per second squared, which yields to 980 kilogram times meters per second squared. Its weight therefore is 980 Newton. Since there is no motion along the vertical, it follows that the normal force is F sub n is equal to weight, which is equal to 980 Newton. We now compute for the maximum static friction by F sub x max is equal to mu sub s times F sub n. Substituting the given values from F sub s max, which is equal to mu sub s times F sub n, we have 510 times 980 Newton, which yields to 490 Newton. To start the motion of the crate, the maximum static friction must be overcome. Hence, the horizontal force needed for the motion of the crate to impend is 490 Newton. If the applied horizontal force is 350 Newton, the crate will remain at rest, given that the applied force of 350 Newton is below F sub s max. Static friction will just oppose it with a force equal to 350 Newton. If the applied horizontal force is 550 Newton, static friction can no longer oppose motion. The crate will accelerate. Applying Newton's second law of motion, which is F is equal to mass times acceleration, acceleration is equal to F sub net over m, which is equal to 550 Newton minus 490 Newton all over 100 kilogram, which is equal to 6/10 meter per second squared. Kinetic friction can be solved using F sub k, which is equal to mu sub k times F sub n. Substituting, we have 1/10 times 980 Newton, which is equal to 98 Newton. For our next example, if the coefficient of friction between a 40 kilogram crate and the floor is 6800, what horizontal force must a worker exert to just start the motion of the crate? If the worker maintains that force once the crate starts to move and the coefficient of kinetic friction between surfaces is 5/10, what will happen to the crate? For question A, to start the motion of the crate, maximum static friction should be computed by F sub s max, which is equal to mu sub s times F sub n, where F sub n is equal to weight which is mass times the acceleration due to gravity. F sub S max is now equal to 6,800 times 40 kilogram times the acceleration due to gravity, 9 and 8 tenth meter per second squared, which yields to 266 and 5600 Newton. Since F is equal to F sub S, F is now equal to 266 and 56 Newton. The horizontal force needed to just start the motion must be 266 and 5600 Newton. To solve for P, first we should compute for the force needed to maintain the crate in moving. We use the kinetic friction F sub k, which is equal to mu sub k times F sub n, which is now 5/10 times 40 kilogram times the acceleration due to gravity, which is 9 and 8/10 meter per second squared, which yields to 196 Newton. The crate will accelerate, applying Newton's second law. A is equal to F sub net over m, which is equal to 266 and 5600 Newton minus 196 Newton all over 40 kilogram, which yields to 1 and 7800 meter per second squared.
Consider an object resting on a horizontal surface. Then slowly incline the plane until the object is in bending motion down the plane. This particular inclination is called the limiting angle of repose, or in simple, we have theta sub r. How is this angle related to the coefficient of static friction? Let us draw the free body diagram of the object. We first resolve the weight into components parallel and perpendicular to the inclined plane. Note that W is equal to F times G. By analyzing the illustration using 6 trigonometric functions of angles, we now have first W multiplied by the quantity of sine theta r is equal to W parallel all over W. W parallel is equal to W sine theta r. W parallel is equal to FV sine theta r. Second, we have W multiplied by the quantity of cos theta r. That is equal to W perpendicular all over W. Thus, we have W perpendicular is equal to W cosine theta r. And we have W perpendicular is equal to Mg cosine theta r. Because motion tends to be downward, static friction must be acting upward in parallel to the inclined plane. Because the object is at rest, it follows that the sum of the forces parallel to the plane must be equal to 0. That is, W sine theta sub r minus F sub S max is equal to 0. But static friction is at maximum. That is, F sub S max is equal to mu sub S times F sub n. Therefore, substituting maximum static friction equation, we have W sine theta sub r minus mu sub S F sub n is equal to 0. Simplifying, we have W sine theta sub r is equal to mu sub S times F sub n as equation 1. Similarly, all forces acting perpendicular to the plane must add up to 0. That is, Fn minus W cosine theta is equal to 0. Therefore, we have Fn is equal to W cosine theta r, which is our equation number 2. Substituting equation number 2 and equation number 1 and solving for mu s, we have tangent theta r is equal to mu s. Theta r is equal to arctan mu s. Suppose we incline the plane a little more. Then the object will accelerate down the plane. To keep the object moving down the plane at constant velocity, the inclination of the plane must be lowered to less than theta sub r. We call this as the angle of uniform slip, or phi. Using the same reasoning as in the angle of repose, it can be shown that mu sub k is equal to tan phi, where phi is equal to inverse tan mu sub k. Note that the angle of uniform slip is less than the angle of repose. It follows that mu sub s is greater than mu sub k.
For our first example, a crate rests on a ramp that makes an angle theta with horizontal. The coefficient of kinetic and static friction is 3500 and 4500 respectively. The inclination of the ramp is slowly increased. Find the angle at which the crate starts to slip down the ramp. Find the angle at which the crate slips down at a constant velocity once motion has started. To solve for A, the angle at which the crate starts to slip down the ramp is the angle of repose. It is given by the equation of angle of repose theta sub r is equal to inverse tan mu sub s, which is inverse tan, which is equal to 4500. That yields to 24 and 2300 degrees. For problem B, the angle at which the crate slips down the ramp at constant velocity once motion has started is the angle of uniform slip, which is given by phi, which is equal to inverse tan mu sub k. By substituting, we have inverse tan times 3500, which yields to 19 and 2900 degree. For our next example, a 100 Newton box is an impending motion down the plane where the angle of inclination of the plane is 39 degrees. Find the components of the weight parallel and perpendicular to the plane: normal force, maximum static friction, and coefficient of static friction. The box slides down at constant velocity when the plane is inclined at 32 degrees. What is the coefficient of kinetic friction between the box and the plane? For problem A, to compute for the components of the weight parallel and perpendicular to the plane, we have W sub parallel is equal to mg sine theta sub r, which is 100 Newton times sine 39 degrees, which yields to 62 and 9300 Newton. Second, we have W perpendicular, which is equal to mg cos theta sub r. We now have 100 Newton times cos 39 degrees, which yields to 77 and 7200 Newton. For letter B, note that normal force is parallel to W sub parallel. To compute the normal force, we have F sub n is equal to W sub parallel, which is equal to 77 and 7200 Newton. For problem C, note that F sub S max is parallel to W sub parallel. To compute for maximum static friction, we have F sub S max is equal to W sub parallel, which is equal to 62 and 9300 Newton. For problem D, to compute for coefficient and static friction, we use the equation for angle of repose, which is theta sub r is equal to inverse tan mu sub s. Manipulating this equation, we have mu sub s is equal to tan theta sub r, where theta sub r is 39 degrees. We now have mu sub s is equal to tan 39 degrees, which is 8100. For problem E, to solve for the coefficient of kinetic friction between the box and the plane, we use the equation for angle of uniform slip, which is phi is equal to inverse tan mu sub k. Manipulating this equation, mu sub k is equal to tan phi, where phi is 32 degrees. Now mu sub k is equal to tan 32 degrees, which is 6200. On your Google Classroom, kindly open the folder with the name Check Your Understanding. There will be 2 sets of exercises that could help you analyze and assess what you have learned from this topic. We have the multiple choice and problem solving.
Thank you very much for watching. We hope that you learned. See you on our next topic. Bye!